Afternoon. First, thanks so much for inviting me to be here. It's definitely an honor and a great event. So my journey started 12 years ago with this question. And the question was, we have greenhouse gas emissions, and we always talk about taxing them or burying them underground. But this is carbon. So what if we looked at greenhouse gas emissions as a resource, and a resource that we could use to make materials? Because if we could do that, in theory, we could create a situation where the world is actually competing for the use of greenhouse gas emissions. And from our perspective, we think that could be a powerful tool. So this was our basic platform. We said, take carbon that's going into the air, but capture it and turn it into a material in a carbon capture process. What we discovered was that when we had this concept, we weren't the first people to have it. In fact, people have had this concept of capturing greenhouse gas emissions to make things for many, many years, many decades. And they came across two major challenges: price and performance. What this means is that when you made this material, it was too expensive relative to materials made from oil, and it didn't perform very well. It was very brittle or just didn't work. So when we started in 2003, these were our two founding challenges. And the single biggest was the cost structure. So when we started, we were taking carbon emissions and turning them into plastic. And plastics, at that point, that were made from carbon emissions were about 3 times more expensive than oil-based plastics. So in a 660 billion pound industry, it's literally impossible for a company, even if they want to pay more for these plastics, to do so on a large scale. And this came down to yield. The way that the process worked was you had to make a kilogram of biocatalyst to make a kilogram of polymer. And at that 1-to-1 yield ratio is just very expensive. So in 2004, we moved into our laboratory at UC Riverside, started working through some of the theories on a small scale. And then in 2007, we built our first pilot line. So this line ran a half a football field in length, 6 major unit operations. But it still wasn't there. We were still stuck at this 1-to-1 ratio. And we didn't know if we'd ever be able to get around it, so we're trying all these kind of different ideas. But finally in 2010, 7 years after we started, we had our major breakthrough, and that was yield. So what we discovered was that this biocatalyst, whereas in the past it would stop at this 1-to-1 ratio, we figured out that the reason it was stopping was it had this negative feedback response. And what that meant was that as the polymer got up to the 1-to-1 ratio, it would turn itself off. And so now instead of making polymer, it would make carbon dioxide instead. What we figured out how to do is blind that biocatalyst so it doesn't see the amount of polymer that's making. And so now instead of making 1 kilogram of polymer, it just keeps going. So now instead of making 1 kilogram, we make 9 kilograms of polymer. So think about that for a second. For the same amount of input, same biocatalyst, we're now making 9 times more material than was made previously. So you can imagine the impact that this had on economics. And you can actually see it. So in this picture, what you see on the left is our Generation 1 pilot line. That was at the old 1-to-1 ratio. After the 9-to-1 breakthrough, we shrank from 150 feet in length to 25 feet in length, 6 unit operations down to 2 unit operations, and finally, for the first time, we had a production cost where we could actually outcompete oil-based plastics on price. So this was 2010. We started working through the theories, scaling this thing up. But in parallel to price, we also had a performance issue. The material we were making was now very cost effective, but it wasn't very performance effective. And there were a number of challenges, from strength, flexibility, color, thermal stability. You ran this stuff and it just went all gooey. So we had to figure out how to fix that. So over the years, we eventually developed a material that exhibits very high strength, very good flexibility, a wide range of applications covering today about half of the plastics market. These are some of the early products that we started to make: different furniture parts, different films, rubber replacements. And 2013 was what I consider to be our breakout year. 2 big things happened. 1, we scaled up to commercial scale for the first time. And 2, we launched our first products to market. So this is our commercial scale production reactor in California. We started this up in August of 2013. And I can tell you that after working on something for 10 years, and the only thing you're working on for 10 years, when we scaled this up, from a reactor that was this size to one that's 50 feet tall, it was one of the most satisfying moments, certainly, of my life. and a tremendous sort of step for the company as far as bringing this technology to life. The second thing that we did was start to launch real products to market. So this is a picture inside of one of our partner companies' plants. What you see, these white pieces of plastic, these are seats for furniture. We're making chairs. This was also very satisfying because many years prior to this day was the day where we ran our initial stuff in and it really didn't work very well. So then to fast forward a few years and to have products where you can't tell the difference between this material, air carbon, and the oil-based plastic that it's replacing was really a great moment for us. We were honored when this product won Popular Science Innovation of the Year last year. In May 2014, Dell launched the first bags made with air carbon. So what they're doing is they're replacing plastic made from oil, and instead they're putting captured carbon that would otherwise go into the air, into their packaging that's actually serving a positive role. So why are companies doing this? There's two big reasons. The first is the environmental advantage. We're taking carbon that would otherwise go into the air, and instead of letting it go into the air, we're capturing it, and we're using it to make a material. But most importantly is the second slide, cost. Because when we started as a company, we said the only way that we can make a truly large environmental impact is if we're also making an important economic impact. So our material actually outcompetes on price, and that allows companies like Dell, HP, L'Oreal's The Body Shop, these different companies that are adopting this material to adopt it in a way where they're saving money, but at the same time capturing carbon. So where are we today? We've got commercial scale production in the US. We've got a unique platform of economics where we're actually out competing oil-based plastics. We've had product launches with Dell, HP, Virgin, Sprint, The Body Shop. And then two big things happened this year. One, we signed a 19 billion pound offtake agreement in June with a company called Vinmar. And just a few weeks ago, we closed on a 10 billion pound license agreement with a Fortune 50 that we'll be announcing shortly. So just to wrap this up, we're now getting ready to build our next large-scale plants, and we're just tremendously excited about the tool that we've got here, where we can take carbon that would otherwise go into the air, capture it, and use it to replace oil. Thanks very much.